floor is yours.
So, hi everyone, my name is Adam Wysocki, and I'll be presenting my research of a strand plane on Lake Superior. And first I want to thank my co-authors that helped me collect the data and helped with the project itself. There's Tyler Aiken, a student that helped with the data collection. There's Harry Joel, who is sitting right there, my faculty mentor. I had Dr. Walter Loop from the USGS helping with data collection, Sean Morrison and August Morin as well helping with the data collection. And I couldn't have done the project without them, so thanks goes to them. And so what I was looking at is what geomorphic processes have formed a strand plane on Lake Superior in the Huron Mountains, Michigan. So what is a strand plane? A strand plane is a series of beach ridges that build out into a body of water over time as two different things happen, as water levels drop or as sediment input increases. And so here's a picture of the strand plane here. We can see that beach ridges, kind of like little hills, are indicated with the white arrows and continue into the background towards Lake Superior. And so that's what these individual beach ridges all together form the strand plane. So we were looking to understand why these beach ridges were forming one after the other after the other. Here's a map of the study area. We can see the counties in Michigan, and the strand plane indicated with green dot or star is located in Marquette County on the southern shore of Lake Superior. Zooming in to the study area itself, the colored lines indicate where the data was collected. We collected 6 different GPR transects, otherwise known as lines. You can see Lake Superior towards the north there. So why are we studying strand planes? Well, strand plane is a coastal feature, and understanding coastal areas is really important because 50% of the U.S. population lives on shorelines, and that population is continuing to grow. In addition, people from these coastal areas produce 58% of the national gross domestic product. So understanding these areas and how they change over time is really important to these people's livelihoods. So looking at the study area, we'll talk a little bit about the Great Lakes, dive into Lake Superior a little bit, talk about the Huron Mountain Club, where the strand plane is located. Looking at this map here, we see the Great Lakes. If I had a laser pointer, I would tell you guys that strand planes indicated by black dots. I'll just get off close and personal. On Lake Superior are located on the southern shore, Lake Michigan, so Lake Huron. Thank you. Let's see, here we go. So Lake Superior, Lake Michigan, Huron, Erie, strand planes are located throughout the Great Lakes. Looking in at Lake Superior itself, it's the largest freshwater lake in the world by surface area. It has great biological importance due to the habitat it provides to aquatic and terrestrial species, and then also is a great economic resource to the region due to the shipping routes it provides to the barges. We can see that the yellow star indicates where the strand plane is located at. Then finally, we were studying at a place called the Huron Mountain Club, which is in the Huron Mountains. As you can see, these mountains pictured in the background right there, and Lake Superior is right there. So this is a private nature preserve about 28 miles northwest of Marquette, and the area is very ideal for studying strand planes and beach ridge formation because it's been preserved from human activity since 1938 by Albert Leopold and other founding members of the Huron Mountain Club. So the method we use to study the strand plane is called ground penetrating radar, otherwise known as GPR. It's a non-invasive method for visualizing the subsurface. So what that means is we're trying to see how sediment layers are structured below the ground surface without ever having to dig a shovel to see those surfaces. So I'll explain a little bit more what that means. So GPR works by having 2 different antennae moving over a ground surface. We have the transmitting antennae that sends out electromagnetic waves into the ground. These waves then go to the surface and reflect off a sediment surface, and then come back to the receiving antennae where the data is then collected and stored in a computer. And then you continue to surface the survey along the ground surface, collecting more data about the different sediment surfaces below. So here's a picture of me and Dr. Walter Luke from the USGS collecting data with the GPR system. There is the transmitting antenna that's sending out those electromagnetic waves, and then Dr. Walter Luke is sending or receiving those waves as well. So why use GPR to study the strand plane? Well, as I mentioned before, it's non-invasive. That means I'm not sitting there for a week with a shovel trying to see what's beneath the ground. That also preserves the data that you're looking at, so you're not destroying it. It saves time and money. You can customize the GPR, or what type of GPR system you're using to what you're looking for. So for example, on the picture here, we see different antennae sizes. We have the higher frequency antenna on the right that has a shorter depth of penetration than what I was using, but it has the data has good resolution. While opposed to, if we want to see further below, we use a lower frequency antenna, but then the resolution is not as good as the higher frequency antenna. So depending on what you're looking for, you can customize your equipment, which is really advantageous in these studies. And then finally, the results are returned in real time, meaning we don't have to sit around and wait for a lab to process some kind of data. You can see it in the field, what you're looking at, and then take that back to the lab and analyze the results. And finally, we also use what's called a laser leveler to collect topographic information. Topography is how a landscape changes in shape overall, and so we want to incorporate that into the GPR data. And to do that, we have the laser leveler set up here. It sends out a laser which you can't see, but indicated with an arrow. The laser reflects off the bolt that I'm holding there, and then comes back to the laser leveler, and that records distance and elevation information. So then the data we're collecting with the GPR, which is flat otherwise, then has the changing topography incorporated with it. That makes the data accurate. Here's some collection parameters that I'll just cover quickly here. So as I said, 6 different lines were collected using what's called the Pulse Echo 100 GPR system. We used an antenna frequency of 100 megahertz with about anywhere between 10 to sometimes 20 meters depth below the surface, mostly 10 though. And 100 megahertz is about the same frequency of radiation used to listen to the radio. We used a step size of 0.25 meters and then antenna spacing of 1 meter. And then we used these parameters below to process the data once we got back to the lab. So here's a 100-meter section of our longest line called NIPRA 1. It was 921 meters long and ran from south to north on Lake Superior here. And if we look at it, we can see that these different black reflections here are the different sediment surfaces the electromagnetic waves were able to pick up. And then I have colored over top of it to make some interpretations. And so looking first, we can see these dipping yellow reflections moving on towards Lake Superior. That indicates progradation, which is the building of a landscape into a body of water, which I'll talk about later. And moving on, we can see we have this flat reflection across the entire profile here. And that's the water table. And then finally, we have that green line below, which is bedrock. So these are some of the things you can start to see with GPR while you're in the field, but this data has been processed a little bit to help with that. Moving along, we took GPR data from the biggest beach ridge in the region, which is called the Nipissing Ridge, to see how the beach ridge looked like below, to see if there's any kind of structure to it. And so we did find that. We saw horizontal lines here, and that indicates what's called aggradation, or the vertical building of a landscape. I'll also talk about that later. And finally, we move into this star-shaped pattern here with 3 different lines pointing in different directions. And these lines, we shot them to see if we could see if the strand plane was prograding or building out into Lake Superior in a certain direction or another. So looking at the line we call lines A, it is directed towards the northwest. And we see these dipping lines, again, similarly we saw before, indicates progradation. Second line, lines B, runs towards the north. We also see these dipping lines and some concordant reflections, which indicate aggradation. So there's more progradation towards the north as well. And then finally, with knife C, indicated towards the northeast, we have a few dipping reflections, some aggradation, but overall the progradation was stronger in the north and northwest lines, so we can start to make some conclusions that the strand plane is most likely building in the north and northwest direction. Finally, I was mentioning the topography that we were collecting with the laser leveler. Here's some of the data from an Excel table with relief and elevation information that's used to create a topographic profile shown below here. And so that's how the strand plane looks overall, shaped with elevation as you go across the surface. Here's where dip PC was located, so that's the biggest featurage. And so every time you see these little humps, most of them are featurages there. And so we applied that data to the GPR data so it would fluctuate just like the landscape does. So after getting these results, now the time came to think about like how the strand plane is forming, what's causing featurages to form one after the other, because it appeared that it was not a random pattern. And so looking at two authors, Thompson and Backey, made a model on Lake Michigan that I'm applying to Lake Superior about how featurages formed. And so this model is based on two things, as I mentioned before, water level change and sediment supply. In Lake Superior, sediment supply is positive. And so we're going to look at, as water level fluctuates, how featurage might be formed. And so starting at point 1, the water level starts to rise. That water level rising erodes sediment, and the water level continues to rise, carrying that eroded sediment further inland. And eventually the water level starts to go down a little bit, deposits that sediment, and that deposited sediment starts to build up over time, causing aggradation, I was mentioning before, with those horizontal lines. And then eventually the water level continues to go down, carrying that eroded sediment back out towards its body of water, or Lake Superior, and that that eroded sediment is then carried further out, which then builds that strand plane or featurage into Lake Superior, which is called progradation. And so that builds one featurage, which then becomes vegetated, which prevents erosion in the future. And so as lake level continues to fluctuate and go through the cycle again, up and down, featurages continue to form. So that's what Thompson and Backey proposed had happened. And so here's what I was talking about before a little bit, to give a little visual on it. If this is a beach face here, and then sediment out in the body of water, as water level starts to come up, it erodes the surface, deposits that sediment further inland, and then as water level goes back down, it erodes the surface, but carries that sediment out towards the body of water, and we start to see some of those dipping lines. So that's what we were picking up a little bit on the GPR. So how can we validate this model a little bit? We can look at the research carried out by other researchers in the study area. Some other people use what's called optically stimulated luminescence dating to determine the ages of these featurages, how long ago they were formed. And so the OSL dating was carried out in these locations on the featurages, and we can see that older featurages are further inland and younger ones are closer towards Lake Superior. Comparing the ages, we see that the featurages form about every 30 years, which Thompson and Backey mentioned about every 30 to 150 years, theoretically. So that helps validate the model a little bit. Lake level change I was mentioning before is very important to the formation of featurages on Lake Superior. And so we have what's called the paleoid hydrograph here. It's a graph of elevation for Lake Superior over time. And if we look back in the past, we can see that lake level used to be a lot higher than it is today, but has gone down overall through time. We can also see these little fluctuations over time as well as water level's gone down. So water level will go up and down, up and down. If we remember from the model, that's how featurages are formed. And that would help explain why we see these featurages on the strand plane building one after the other, as water level is fluctuating over time. And then finally, we needed a sediment source to build the strand plane. So looking at some other research, found that Lake Superior's currents go in a counterclockwise motion around Lake Superior. So I propose possibly that The sediment source would be the Keweenaw Peninsula here, circled in blue, and the eroded sediment would then be transported to the strand plane down here. So in conclusion, the strand plane is demonstrating a cyclic pattern of propagation and aggradation. That pattern is influenced by lake level drop, Lake Superior's currents, other factors as well, and then the information gained from this study helps water resource managers, city planners, and shoreline residents better understand the environments in which they live, which is important to their livelihood and the livelihood of other people as well. So I'd like to acknowledge EW Eau Claire's RSP program for providing funding for the data collection this summer through the summer research experience for undergraduates. I'd like to thank the Student Travel for presentation of research results for research conference travel. The Simpson Fund and the Geography Department also helped me go to research conferences. The Huron Mountain Wildlife Foundation helps provide financial and logistical support. Gamma Theta Upsilon helps provide funding for data collection and research conference travel. And then Sensors and Software, the GPR company, helps with the processing of the data. So, thank you.